The goal of this video is to introduce ourselves to logarithms. Well, logarithms basically are the combination of the last two things we've done. A logarithm is the inverse of an exponential. So we dealt with inverse functions back in 2.6. And then we played with exponential functions in 4.1 and 4.2. Now we're looking at the inverse of an exponential. And so we're going to think about it first by domain and range. And let's compare them. Exponential functions had this, so logarithms will have an equivalent over here. Let's make that line the whole way across. Exponential had a domain. Now this is non-transformed exponential, so it's b to the x. Had a domain of negative infinity to infinity, which means logarithms will have a range of negative infinity to infinity. Remember, the domain and the range between a function and its inverse just switched places, which means the exponential function's range of 0 to infinity gives us a domain of the logarithm 0 to infinity. Now again, remember this is a non-transformed logarithm. We will have to play with domains a bit more intensely later on. Exponential functions always contained the point zero, 1. Because if I take b and raise it to the 0th power, I get 1. So I should have said equals y. Well, then the logarithm, how did we switch from a function to its inverse? We swapped x and y, so it contains the point 1, 0. By the same argument, I'd say the exponential contains the point 1b, because b raised to the first power is b. It doesn't matter what b is. So the logarithm would contain the point b1. Swap x and y. The exponential had a horizontal asymptote on the x-axis, which means its equation was y equals 0. Well, if we swap x and y, we're going to get a y-axis asymptote, x equals 0. That means it is a vertical asymptote. And then in general, if we remember our inverses, if we have f of x equals y, well, that means f inverse of y equals x. Remember, it just undoes what happened before. The inverse simply undoes what the function did. And so specifically, that means, well, our original function was an exponential, so we had something like b to the x equals y. Well, I'm going to change it a little bit. That's equivalent. This symbol is equivalent to. So that's equivalent to saying log base b of y equals x. And now notice I read that log base b of y equals x. And that is important. Saying log b to the y or log of b to the y is actually something completely different. We will look at that a little bit later on. This is log base b of y equals x. Okay, So, let's play with that a bit. For example, if I have 5 to the 4th equals 625. Go ahead and double check that that's correct. You can pause the video. Well, if I have that, according to what we just said, this is equivalent to writing log base. Ooh, what's my base? Well, in the exponential, the base was the thing being raised to a power. So my base was 5, which means my base of the logarithm is also 5. Notice this is written as a subscript. The base of a logarithm is a subscript. And then x and y switched places. Here y was on the opposite side of the equals sign for my function. Here y is the input of my function. So it was on the opposite side, 625. That means we want log base 5 of 625, and that's equal to our previous input, which was 4. So all logarithms do is undo exponentials. For example, let's evaluate log base 4 of 64. How am I going to do that? Honestly, I don't think about logarithms by themselves. I always think about them as exponentials. So what I'm going to do is I'm going to think about it as if I wrote log base 4 of 64 equals, we'll say x. And then I'm going to rewrite this as an exponential. So what's my base? Right here, it's 4. And now these trade places. So instead of log base 4 of 64, I want 4 to the x. And it's going to equal 64. These two are equivalent statements. Saying log base 4 of 64 equals x is the same thing as saying 4 raised to what power is equal to 64. And I didn't even really need that equals x. I needed it in order to convert equations, but I didn't need it up here. All I had to do was look at log base 4 of 64 and say, well, 4 raised to what power equals 64? And that power is, of course, 3. So x equals 3, which means log base 4 of 64 is equal to 3. Okay, a couple more things to do about logarithms. First of all, there are two specifically named logarithms. One is called the common logarithm. And that looks something like this. Well, I'm going to do it as an example. We're going to evaluate log of 10,000. Ooh, what do? I don't see a base here. We're missing a base. Well, whenever we see the word log with no base, this is the same thing as saying log base 10. And that's what we call the common logarithm. Log base 10 is common enough. It's just like with square root. With a square root, you'd write the radical sign. So you'd write that radical without any index here, and we know that means 2. That's our common radical. Well, our common log is base 10, so we will write it without even bothering to write the base. And now we ask 10 raised to what power is 10,000? Well, with 10, that's easy. We just count the zeros. And that is 4. The other one is called the natural logarithm. And it looks like this. I'm going to write it purely as an equation. Y equals natural log of x. And this is read, quote, natural log of x. Well, the equivalent exponential form, what's the base? When I see ln, the base is the natural number, e. So that's the same thing as saying e to the y equals x. In the natural logarithm, there's a button on your calculator that will help you evaluate that. So let's look at a new page and now try to graph. How about we graph h of x equals log base 6 of x. Well, how am I going to do that? There's a few things we had from last time. First of all, we know the domain is 0 to infinity. We know there's a vertical asymptote on the y-axis. So let's draw my axes over here. Well, I know I've got a vertical asymptote on the y-axis. I know my domain is 0 to infinity, so I know I don't even really need that negative x-axis there. We know it goes through the point. Oops, that's exponential. Exponential goes through 0, 1. So the logarithm goes through 1, 0. Then I claim it goes through b1. Why is that? Well, log base 6 of 6. I would be asking 6 raised to what power is 6? And that is 1. So 1, 2, 3, 4, 5, 6, 1. It's an increasing function still. So it will look something like this. And we can do any transformations we want. Just watch out. If I sketch instead g of x equals log base 6 of x minus 2, we need to be careful. Order of operations tells me I take log base 6 of x first and then subtract 2. So this 2 here is a vertical shift down 2. So that means we would take this function that we've just graphed, let's make it blue, and move everything down 2 spots. And we end up with something that looks like that. If I meant it to be a horizontal shift, change colors again. I would need something like f of x equals log base 6 of, in parentheses, x minus 2. That will now be a shift to the right. So just watch out for those parentheses. It's really easy to mix this one up. One last little detail. Let's worry about the domain of a logarithm. Well, didn't we say it's always 0 to infinity? That would be non-transformed. Let's look at this one. I have moved it to the right 2. That means if I played with it on this axis, 1, 2, 1, 2, well, the asymptote also moves to the right 2. So it is right here. We have a graph that looks roughly like that, whose domain is clearly 2 to infinity. So how do I play with that? Well, what matters is that the inside of the logarithm, the input, is positive. So it doesn't matter if x is positive or not, just the input. Example, log, we'll do a common log, 7x plus 35. What's our domain? Well, we need 7x plus 35 to be greater than 0, so 7x must be greater than negative 35. So x must be greater than negative 5. Whoa, negative 5, which means our domain is negative 5 to infinity. Thank you for watching.